Ever since OpenAI unveiled ChatGPT in 2022, it has started a sort of arms race between companies to release their own versions of large language models. Every new startup these days seems to be just a glorified ChatGPT wrapper. Every company has been trying to find ways to shove AI down employees' throats. There are smart TVs out there that come pre-installed with Copilot for some odd reason. Everywhere you look, you're assaulted with AI-generated images, videos, art, to the point where it's sometimes hard to tell what's real and what's not. There are people in really problematic relationships with AI. Others are having delusional episodes triggered because they spend so much time talking to AI agents. So ignoring any sociological criticisms of AI, a common criticism that you will hear is that AI uses a lot of water and energy compared to the standard Google searches, for example, that we used to have back in the days, like 4 years ago. It seems that Sam Altman has also heard this criticism and revealed in an article in June 2025 that an average ChatGPT query uses 0.000085 gallons of water. On the other hand, the Washington Post did their own research and noted that to generate a 100-word email, ChatGPT uses around 519 milliliters of water, which is around half a liter. So that's 1,500 times more water than what Sam Altman is claiming. But I'm not here to debate the exact numbers. I want to explain why water is being used in this process in the first place. Not counting the water that it takes to generate the electricity that's being used in the data center, where else could the water be needed? The answer is simple: cooling. You see, mechanical cooling in any form works the same way. It's all about moving heat from one place to another. Under normal conditions, things want to reach an equilibrium. That is to say, heat wants to move from a place of higher temperature to a place of lower temperature. Now, in order for this process to move in reverse, you have to input some form of energy into that system. This is done using the refrigeration cycle, where a specialized refrigerant is cycled through a closed system of compressors and expansion valves to move heat. Think of a window AC that you might see in a typical apartment building. The window AC is essentially moving heat from inside of the room to the outside of the room to make the inside colder. There are two key components of the refrigeration cycle we need to know here. The first is the condenser. This is where the hot gaseous form of the refrigerant is condensed into a liquid form by removing heat from it. The second is the evaporator. This is where the cooled liquid form of the refrigerant is evaporated, as the name implies, by adding heat to it. In essence, if you have the evaporator inside of a room and the condenser outside of a room, you will move heat from the inside to the outside. The opposite is true if you switch their locations. Now that we have that out of the way, we can discuss how data centers are typically cooled. Data centers are buildings or parts of buildings that are used to house servers needed for cloud computing services that we all use. They form the invisible backbone of the modern internet. For example, the photos you upload to Google Photos or OneDrive are stored at Google or Microsoft servers located inside of a data center. Also, the image processing and facial recognition performed on your stored photos on Google Photos, for example, is also being done on the computers in the data center. When a computer performs calculations, it uses electricity. For instance, my personal computer that's sitting right there draws about 140 watts of power for its CPU and 200 watts of power for its GPU. This power draw is directly converted into heat. Using my computer as an example, that's enough heat to bring a liter of water from room temperature up to boiling in about 15 minutes. This is why personal computers contain fairly sophisticated air cooling systems inside to dissipate heat from the CPU, the GPU, to the ambient air of your room. I mean, gamers will know that if you leave this computer running in your room in the summer and you're gaming, your room will get fairly hot. On a commercial scale, the power draw and heat dissipations of data centers are much, much larger. According to ASHRAE, the power density of an average IT rack in a data center used to be around 4 kilowatts per rack. But with the advent of AI, this has jumped up to anywhere between 12 kilowatts and 30 kilowatts per rack, and even higher. For data centers with such high power density, the best option for cooling is actually a chilled water system as opposed to an air system. And this is where the water consumption really comes in. The principle of a chilled water system is simple. Consider a closed loop of pipes, complete with a set of pumps that continuously cycle cold water throughout a building. This cold water has a temperature anywhere from 6 to 10 degrees Celsius. At each room containing server racks, you can either take a branch from this chilled water loop and feed this water directly to the server racks for direct liquid cooling, or more commonly, you can pipe this chilled water to a fan coil unit that essentially circulates the room air through a cooling coil that's going to contain this cold water. With both of these approaches, you essentially cool down the servers and transfer that heat from the room and from the servers directly into the chilled water. So as this water circulates through the building, it collects heat heat from all the servers that are in the building, and that increases the temperature as it circulates. Now the question is, how do you maintain the chilled water temperature to its normal range of 6 to 10 degrees Celsius? So the answer here is simple. You use the refrigeration cycle. So the chilled water that's returning from the building, we call that return chilled water. It's actually now at a higher temperature than what it left at because it collected all the heat from the server racks. So now what we do is take this return water and process it through a piece of equipment called a chiller. As the name suggests, the chiller removes the heat from the chilled water return. That's essentially the evaporator in the refrigeration cycle. And it transfers the heat to the condenser side, right? So it's going to cool that chilled water, and on the other side, it's going to heat up a different medium. On the condenser side of the chiller, you have a set of pumps that circulates more water to collect that heat from the chilled water and is heated to something like 40 degrees Celsius as this heat is collected. Although this depends on the particular design of the system. So here's where the water use comes in. So far, we've talked about closed loop water circulation inside of the data center. So inside of the building, the water is circulated in a continuous closed loop in the form of chilled water. So therefore, no water is actually lost from inside of the building. However, on the other side of the chiller, the condenser water is actually not a closed loop system. It's an open loop system. So the goal here is to take that heat that the condenser water has collected from all that water inside of the data center and reject it into the atmosphere, so into the ambient air. And that's done through something called a cooling tower. And no, I'm not talking about the giant chimneys you see near nuclear reactors. That's a different type of cooling tower. I'm talking about these things you will see on the top of many high-rises, hospitals, and of course, data centers. The principle of operation for a cooling tower is simple. Water requires what's called the latent heat of vaporization to evaporate from liquid form. When water evaporates, it essentially sucks the required latent heat of vaporization from the surroundings in a process known as evaporative cooling. It's the same reason humans release sweat, for example. If you've ever noticed while you're sweating and you blow some air on the skin with sweat on it, you'll notice a cooling sensation on your skin. That's essentially because the water, your sweat, is evaporating and kind of sucking the heat away from your skin. In order to reject the heat generated by the data center and to cool the condenser water down, an open cooling tower turns the entering condenser water into a fine mist, essentially increasing its surface area. Then the cooling tower fans blow atmospheric air up through the mist, evaporating 1 to 2% of the total mass of the condenser water. This evaporation results in an overall reduction in temperature for the rest of the condenser water. The remaining water is then circulated back through the loop again to collect more heat from the chiller. So as you can see, 1 to 2% of the water is lost in the process every time the water goes through the cycle. And this water has to be made up by a fresh water source continuously. According to the Uptime Institute, a 1 megawatt data center will pump 855 gallons of condenser water per minute through a cooling tower. Accounting for a 2% loss of water means that 17.1 gallons per minute of water is being used per megawatt. And that's just 1 megawatt. Companies like Meta operate data centers such as this one in Louisiana, which is over 2 gigawatts. Now, I can't tell you if this amount of water usage is worth it to generate some videos of babies dancing or deepfakes of Elon Musk selling Bitcoin. That's for you to decide on your own. But I do hope that this has been a useful and informative video for you. As always, take care and stay curious.